A very good morning, everyone. Our speaker for day 3, session 5 is Dr. Upendra Mohan Bhatt, a visiting assistant professor, BITS Pilani campus, renowned for research and academics in microelectronics and VLSI. Now, further, I would be requesting FDP coordinator Mr. Rajesh Singh Shekhawat to welcome our distinguished speaker with the bouquet. Dr. Bhatt did his PhD in the field of microelectronics and VLSI from the Department of Electronics and Communication Engineering, IIT Roorkee, Uttarakhand. He has been offered postdoctorate research fellowship by the Institute of Computer Architecture and Computer Engineering, Semiconductor Test and Reliability at the University of Stuttgart, Germany. He has worked as cooperative with the Applied Materials Incorporated, MA USA. His key publications include three research publications in IEEE transactions on electron devices and conference paper in SSDM International Conference 2018 at University of Tokyo, Japan. He has a total citation of 62. Without further delay, let us warmly welcome to the stage Dr. Upendra Mohan Bhatt, who will be sharing his expertise. Sir.
हेलो वर्किंग ओके क्या करना इसमें भी ऑन नहीं है ओके this has to be turned off okay so am I audible so good morning to all of you so first of all I would like to congratulate and thank the organizing team for organizing such a good event. Such events should be organized regularly in the institute regarding development and research. Okay, and now without wasting too much time, I would like to start my talk. So the topic that I had decided is charge trap based 3D NAND flash memory. So it looks quite like amazing what different terms are there. Charge trap based, then 3D NAND flash memory. So flash memory, I hope you all are aware of that. Like our pen drives. Nowadays there are SSDs, solid state drives. So and I mean the class of non-volatile memory that where we can store our information for around say 10 years. So that is my core topic of this talk. However, as per the discussion held, I was means you can say suggested to begin with some basics, and later on I will arrive at that point. So I will start the talk with some basics, and then we will come to the that 3D NAND flash memory. What is that, and then what is charge trap there? Okay, so that's why overview I have started with a 0 point. 0 point is basics, right? The building block for our talk. Then I will discuss introduction to the NAND flash memory. Why do we call it NAND? All those things. And then I will come to the core topic. That is you can say my research area, that work that I have done. What were the technical gaps earlier, and then later on what I did using TCAD simulations, certain characterization work as well as means in US with applied materials, and then I will discuss performance enhancement, how we can enhance the performance in terms of current and program erase window. What are those again? I will discuss later on. I will discuss again tapering. What is that? And in means in every point we will discuss how to mitigate the shortcomings. Finally, we will conclude and some future aspects. Okay, so as I could read the means topic of your FDP is the tagline for that is semiconductor excellence. So I would like to start with this. We all are aware of the fact that electronics is everywhere. Without electronics, no other branch is able to survive. Whether it is mechanical, that it is civil, even computer itself is an electronic device, electronic equipment. So we know the importance of electronics is from solar energy up to our mobile phones and much more. So there is no need to explain that too much. Also, one point I would like to add as per the topic again, semiconductor. So we are well aware of the fact that we have three classes of materials: insulator, conductors, and the third one is semiconductor. So the very important property of the semiconductor is that we can change its conductivity. We cannot do this with metal or insulators. This can be done only with semiconductors, and you know that how do we do? We do doping and other methods are there like temperature, okay, sunlight, so light energy, thermal energy, doping. By those methods, we can modulate the conductivity of semiconductor. This is not possible with others. So that is why there is importance of semiconductor. They are found in every chip nowadays. So that factor that we call that method as conductivity modulation. So that is the importance of electronics and this semiconductors. Okay, now moving on to our basic part. So I could start from like basics, device physics and all that. We have diodes, we have metal semiconductor junctions, we have much more. So I decided to start with at least say MOSFET, basic MOSFET. So will that be okay? Yeah, because it is not possible to cover like diode and transistors, and also it is not good enough to switch directly to my PhD research or my current ongoing research. Okay, so I try to make a balance as per my justification. It might not be for all of you, so we will have to cope up with that. So I started with a simple MOS. NMOS, PMOS. I hope we are aware of these terminologies: metal oxide, semiconductor, field effect transistors. Okay, so we don't have like marker and this thing. Means everything will have to go like this. Okay. Okay, so this structure shows NMOS and a PMOS. So we all know that transistor, this metal oxide semiconductor field effect transistor, they have generally four terminals: gate, source, drain, okay, and one body. In this picture, we can see that there is a P substrate. There is a P substrate, this one, and both NMOS and PMOS are fabricated. So how that is done, I hope we are aware of those factors. That how NMOS and PMOS are fabricated together. That we call CMOS, complementary, right? So, but in the same substrate, how that is done? So, if it is P substrate, it is very easy to like fabricate NMOS. Obviously, there is P substrate. We will design all these gate, source, drain, and also body terminal. But what about PMOS in the P substrate? PMOS in the P substrate. So, what we do? We will make an N-well separate. Like we can, how will we make N-well? By doping, maybe diffusion or ion implantation. Then this will become a substrate for the PMOS. This N-well will become a substrate for that, and again accordingly we can design the source, gate, drain, body. And obviously we know if this is N-channel MOSFET, the source and drain will be heavily doped N type. If it is P type, the source and drain will be heavily doped P type. Okay, so this picture shows like an overview of how that was done. The previous, how that structure was achieved. So I think I will not go into this much of depth. You can grasp those things. How do we arrive at the this structure, right? Further, there is one more technique. What we do is that this is also called twin tub technology. In order to get better electrical performance of the devices, what we do, and proper isolation, what we do is we start with uh, this say N-type substrate, for example. Here again we have both NMOS and PMOS. So suppose this is N-type substrate, it would be lightly doped, say 10 to the power 14 per centimeter cube. Then epitaxial layer is grown over this. So I hope you people know this. So this would be from the crystalline substrate, crystalline silicon that would be lying here. Then we will grow epitaxial layers of the silicon. Then we will develop N-well and P-well. Now you know why N-well and P-well. Again the same concept. N-well for PMOS, P-well for NMOS, right? I try to say just summarize those steps so we can see the first part. See, there is N substrate, can be seen. Over N substrate, epitaxial layer is grown. Then, after that, what is done? SiO2 layer. So now, what we will do? We will oxidize this silicon. Oxidation, and then so we are you getting? We are trying to achieve this structure, and I will discuss fastly, right? So we have discussed up to this point. Yes, then what we will do? Where were we? SiO2 layer. Then what will we do? We will etch that SiO2 layer at this point and at this. Why? What will I do? I will have to implant now N-well and P-well. So see, we can have these two portions are etched with proper masking. Now I will put a photoresist here so that nothing is implanted here. And now we will implant P plus from this side. P plus means we want to make a P well. And the next step will be reverse of this. That is make photoresist, apply photo mask here, which will prevent end dopants here. Okay, and then we can make a N well. I hope it makes sense. Yes, so then we will deposit this SiO2 over here. Okay, and in this way, now we want to make N channel MOSFET and P channel MOSFETs on those wells. So see, so this is covered with photoresist. I will implant source and drains forward for a PMOS. Okay, similarly, then we will cover this side. We will implant source and drain. That is N plus for the NMOS on P well. So now we have arrived almost. What will we do now? We have to make metal contacts for the outside connection. So we will do like this, metallization we call this. But now see, everything is sorted out there. Everything is sorted there. Sorry. Okay. So now we need to remove the unwanted metal from there. Yes. So this we will remove that, and finally we will arrive. Yeah, we have removed the unwanted metal parts, and we will arrive. So this is very, you can say, basic example of how fabrication is done, right? Although this is not much simple, that much simple that I stated. Process is very complications are there. We need, nowadays we have like automated design, but okay. So now after that, before switching to the proper working or means VI characterization of this, say this is N channel MOSFET and P channel MOSFET. First, we will simplify the structure by removing too many terminals from there. Like we will remove this source from here, drain from here. I will cut it like this. I hope you are getting. I will cut it only for two. I will make it a two terminal device by cutting along this gate and that P well only. That's it. And in between, you know that we have what? We have this oxide. This is metal, that is contact. Okay. So we will discuss simply how a two terminal MOSFET behaves. So as I discussed, we have cut it along that direction, right? So we have metal only, then we have oxide, and then we have P-type silicon. Now, what do we expect? What should happen? I mean, why? I hope you know why we have designed MOSFET, right? Applications of MOSFET, like it is used as a switch, it is used as an amplifier, used in analog circuits, used in digital circuits. But before like switching to those circuits directly, we should know how a MOS structure will behave. So there are, say, work functions. I hope everybody is aware of the terms like work function of metal, work function of semiconductor. So work function means whatever energy is required to take an electron just out of that material, whether it is metal or semiconductor, means it is free from that material now. So the energy required, that energy is called work function. Okay, so there will be some difference in the metal work functions of this metal, this metal and sim. We are not concerned about oxide, obviously. Oxide means insulator, so now this. So now I am not aware of the fact that how many people are aware of these terminology like energy band diagram. So should I discuss? Everything, whatever you want to discuss, because it is like from the different fields. So all are not from the semiconductor side. Some of them from the computer science also, some of them from the chemistry also. So it means you may discuss each and every topic. So it is not like that. Yeah. You can explain anything. Okay. Some of these structure is not new for me, but it is, this structure may be new for some of them. Okay, okay, okay. Okay, so what we are trying to do is we are trying to analyze a MOSFET behavior, right? But we cannot directly analyze it. We will go step by step. So in VLSI, in our domain, it is said that if we are not able to explain any phenomena without an energy band diagram, then we know nothing about that topic. Right? So that's why we have to follow this energy band diagram and every concept becomes clear from here. As I said, work function. So this side is we have metal, right? This side is metal. That's why I wanted some like marker. So we have metal here. Now the energy required, this is called Fermi level of the metal, means we will find electrons maximum up to this point, probability of finding electron in metal, and the energy required to get that electron out of the metal, this part, this one. So this is called vacuum level, the top one, vacuum level, right? Now, in this situation, we have assumed an ideal MOS structure. Ideal means work function of the semiconductor and work function of the metal, both are same. Now, what is work function of the semiconductor? So, in semiconductor, so even computer science students, they know what is energy band diagram, right? So, we have conduction band as valence band as, now the Fermi level is there. If it is closer to the valence band, it will be a p type. We have an intrinsic level as well, means without doping, right? Intrinsic semiconductor. So that energy, that intrinsic energy level lies at the mid. So if it is a silicon semiconductor, then this gap between EC and EV, we know it is 1.12 electron volt. So up to this middle one, we have half of that, 0.56, right? And this is Fermi level. Fermi level, from where does this come? Why this Fermi level is shifted? Because of doping. So due to doping, what happened? We have introduced acceptor ions, acceptor atoms. Now what will an acceptor atom do in the semiconductor? Acceptor atom will accept one electron and resultant will be one acceptor ion plus one hole. Now actually we are short of electrons. So that's why Fermi level will come down, because it says probability of finding an electron, right? Fermi level. So Fermi level will come down and it will come to closer to valence band because we have more holes now in that same semiconductor. So here we have assumed ideal structure. Ideal means there are no surface charges and charges inside the oxide, and work function of semiconductor and metal both are same, means equal amount of energy is required to get an electron out of the materials both. So if this is the situation, which is not the practical case. Now see what will happen if we will apply some voltage. Say I will apply suppose some positive voltage at the gate under this situation. Now what will happen? What is going to happen is positive voltage at the gate. Suppose I have applied say plus 5 volt here. What will happen? So we know very well inside metal there is, what is the electric field inside metal? Zero. Voltage drop will be ideally zero. The entire 5 volt has to drop in oxide and in semiconductor, right? So suppose roughly I'm saying it is not the case. Suppose 75% of the voltage is dropped across this oxide, then remaining 25% potential of that 5 volt it is there. Now what will happen? So suppose this surface, this surface is positively charged, right? At least 25% positively charged. What will happen if it is positively charged? What will happen actually? So electrons, yes, yes. So electrons will start piling up at the surface, not away from the surface, at the surface only, right? So we know very well whenever electron concentration is getting going to be changed, the band will, yeah, it will change its position. So suppose there are more electrons, so where should this band bend? Suppose we have more electrons here. Now what will happen? Band will come down, it will come closer to Fermi level. Why? Because electron number has increased, right? And accordingly the gap has to be maintained equally, so valence band will also bend. In fact, intrinsic level has to stay in the mid of conduction and valence band that will also bend. Okay. However, if we do reverse, earlier I said positive voltage at the gate. Now, if we will apply negative voltage at the gate, then what will happen? If I will apply negative voltage here, what will happen? We can say electrons will be repelled from the surface, or we can say holes will be attracted at the surface. So electrons getting away from the surface means that distance between Fermi level and conduction band will increase because electrons are getting away from that. Okay, but not deep in the substrate or that silicon silicon, just at the surface we are talking about. So means we call this as the band bending, and whatever is the amount of bending in the oxide, accordingly, yeah, everything will bend except for the Fermi level. The bands will bend accordingly for the oxide also. So that net bending for the oxide is that we will call as voltage drop across the oxide in terms of energy multiplied by Q. That much of energy is you can say absorbed by the oxide. So that is a basic, very basic concept. Now I think again this is common to all of us in first year engineering also. First year level, everybody goes through these concepts, right? So we know in semiconductors what happens at under equilibrium. Under equilibrium, the product of electron and hole concentration is equal to the square of the intrinsic carrier concentration, but this is generally valid under equilibrium conditions, not under excess carrier condition. Then NNPR electron hole concentration, right? Ni is the intrinsic. Intrinsic means again without any doping. Okay, so I hope you know that concept. For example, in silicon at room temperature, not at room but at 300 Kelvin, around 25, 27 degrees centigrade, it is 1.5 into 10 to the power 10 per centimeter cube. So at this point, so there is a mistake here. Sorry, this is 1.45 into 10 to the power 10. Now here I have it like just a point of discussion. Suppose temperature is made to 0 degree or 0 Kelvin, ideal, everything is freezed out. What will be this concentration? If everything is 0 Kelvin means everything freezed out, what will be this concentration? That's why every time we write here 300 Kelvin. If we will make it 0 Kelvin, this will go to 0. All the electrons they will they will be well tracked in the bonds, covalent bond in the valence band, right? Nothing will be there free, no free electron will be there in this case. So as temperature increases, covalent bonds break, and for every bond breaking we have one electron, one hole. That means we can say that around this number of bond has been broken at 300 Kelvin. So if we have a p-type substrate, just like in n-channel MOSFET, and it is doped up to say 10 to the power 15 to 10 to the power 16 per centimeter cube. So what will be the number of hole concentration? Approximately equal to that doping level, right? And what will be the number of electrons, which are called minority carriers in p-type substrate? That will be Ni square by Na. That is from this concept. Now, I have separately drawn this energy band diagram of a p-type substrate. So now there are certain terms, like as I said, band gap is there. This is between conduction band and valence band, 1.1 electron volt. This electron affinity is also there. Electron affinity is the energy which is required for the electron to get it out of the semiconductor, but from where? From conduction band, right? So that's why its work function will have these terms: chi, q chi, we call that chi electron affinity, plus up to here. And there is another term called Fermi potential. So if there was no doping in the semiconductor, what was there? Conduction band, valence band, and this intrinsic level. Now we dope it. Now we dope it, Fermi level is shifted. So this shifting of Fermi level is basically referred to as what we call Fermi potential. Means the potential developed because of the shifting of Fermi level is called Fermi potential. And for a p-type semiconductor, simply what is the Fermi energy shifting? Ei minus Ef, Ei minus Ef. So Q into phi f is Fermi potential multiplied by Q. I hope everybody know that relation, na? Energy equal to voltage into charge. Yes, so this phi is in phi f is in volts multiplied by Q, it becomes energy, right? So Q phi f should be how much equal to EF minus EI in case of N type semiconductor. EFY, because in case of N type Fermi level lies above. Okay, so finally this formula for this Fermi potential is kT by Q ln ND upon Ni in case of N type semiconductor. Here we have drawn it for P type semiconductor. So what will be the formula for P type semiconductor? For P type semiconductor, same kT by Q ln this Ni upon Na, or we can say a minus sign here, minus kT by Q ln Na upon Ni. So these are the simple things. This is already discussed. All these points I have already covered, right, in the previous slide. So this is the work function of that silicon. Can anybody tell me this is for N type or P type? This part. Yes, N type. So in N type we have Q chi from conduction band up to the vacuum level, and after that this Fermi level, only thing remains is Fermi level below conduction band. So this is for N type. For P type, what would be this value? Work function for P type, Q chi plus band gap by 2 and that distance remaining, that is Ei minus Ef. Okay. Now this is the energy band diagram for a MOS structure. So now metal oxide semiconductor. So we have one is free space energy that we call vacuum level energy. This is Fermi level for metal. For example, consider this like maybe aluminum we say. So 4.1 electron volt of energy is required for this in case of aluminum, right? So I will call it as work function of this metal is 4.1 electron volt. Now in case of oxide, so before oxide come to this semiconductor. So in semiconductor we know now what is this energy band diagram, how does it look like. We have this electron affinity, so 4.15 electron volt. This is a case of silicon, right? Now see oxide, is there any special thing about the oxide? Yes, it is clearly observed. What is that? The gap between valence band and conduction band is very large, much large. We cannot shift an electron with some like techniques to shift it from valence band to conduction band. If we will try to do so, ultimately what will happen? Oxide will get damaged, right? And you can see only if we are able to do that, then only this much of energy is required for the electron to escape. So this is the basic band diagram of metal oxide semiconductor when they are not in under equilibrium. Just we can say they are just touching each other, not under equilibrium. So under equilibrium, what will happen is the first foremost thing is what will happen. I hope everybody means we know that Fermi levels will align. See, this is the you can say a bound rule in VLSI that under equilibrium Fermi level will align throughout when the metals or semiconductor they are in contact. So see, if this Fermi level has to get aligned with this Fermi level, then obviously what will happen? Fermi level will stay a constant throughout. So what needs to be done now? In case of semiconductor, there will be some band bending. In case of semiconductor, there will be some band. Can anybody tell me at this moment where will the bands bend in the semiconductor? And what is going to happen in this situation? So work function of metal is smaller as compared to work function of what? Semiconductor. What does this mean? What will happen? What is the probability now? That means from metal we can easily get an electron out, right? So when we want to establish thermal equilibrium, it is not like we are taking 3 bars and going outside this room or in this room and just touching them. No, they are under some processing. I hope you are getting. They are under some machinery where there is some particular temperature, pressure is maintained. What will happen? So it will happen, what I guess is electrons will get shifted towards this side because here only small amount of energy is required in case of electrons to get out of it. So electrons will get shifted towards this way, this side. Right? Forget about the mechanism, how they will get shifted. That is not the point of concern. But what will be general tendency? Lesser energy is required here, right? More energy is required here. This much of energy is required in this case. So it is better and easier, right? So what will happen? The point is that what will happen? So when electron will get shifted in p-type this material semiconductor, so p-type semiconductor has what more a majority of holes. Obviously what will happen at the surface holes will get depleted of first. Yes, under equilibrium, in order to establish under equilibrium means there is no further movement now from one side to another. So what will happen? These electrons will we can say deplete holes in the p-type substrate, and at the surface we will have depletion at the surface only. So depletion of holes means where will the band bend? Where will the band bend? This valence band will get away, right? This valence band will get away from the Fermi level. Why? Why? Because we are depleting holes at the surface. I hope this concept is clear, right? So at the surface only, the distance between valence band and Fermi level will increase. Away from the surface, it is limit that effect will be neutralized at the surface only. Or to be very specific, it depends upon the depletion width up to where the surface is depleted. Okay. So basically you can say read out these points if you are interested in, say, when we combine MOS, Fermi level must line up, as I said. That is the hard and fast rule in case in a VLSI. We have to follow that. And because of work function difference in between semiconductor and metal, there will be voltage drop across MOS and bands, as I said. What I said, there will be band bending here. Accordingly, bands will bend for oxide. And please note down one more thing. Whenever there is band bending, there means there is electric field. Right? Whenever there is band bending, that means there is electric field. If there no bands are bending, that means electric field is zero. That is another point. So here see, under this situation, electric field is zero in the semiconductor or in this oxide. Right? Band bending means electric field. And one more rule: current flows means Fermi level will not be same. Yeah, yeah. Can we change the metal? We can change. Yeah, yeah, please.
Sir, can we change the metal?
Metal.
Metal, aluminum. Aluminum.
Yeah, yeah.
So can we change it?
Yeah, yeah, we can change it. It depends upon like our requirement and the design application.
Suppose, sir, at the place of aluminum, we have changed it or replace it with the help of copper. Okay. Then what will be changes in the Q5 5M?
in the Q?
pi m.
Yes, so what is the work function of copper? It depends upon that. So what is work function of copper? I don't memorize it right now. Copper has a larger work function than this or not? Or no? You can please tell me the value of copper work
Copper.
function.
Yeah.
Is it more than that? So only change will be that. Suppose copper has larger work function, right?
Right, sir.
So suppose it goes up to this point.
Okay.
So that means the same process will take place again, but up the band bending will go on reducing. See,
Then sir, the Fermi level will change.
around 4.5 na. Okay, so shift this line accordingly, right? This line will be
Okay.
shifted accordingly, and now you can see this Fermi level and this Fermi level will come
So the
closer.
sir Fermi level that will be nearly equal to the valence band, right, sir?
Nearly
Or
equal to the
valence band.
maybe you can say what is this sorry, so can we please can you count this here 4.15. See, I got your point. If anyhow you are able to bring this down
Yes, sir.
below this, then reverse will happen.
Then we do reverse.
Yes,
Okay, sir.
exactly. If the metal work function goes below this, then reverse will happen. Reverse happen means that there is tendency of electrons to get in the metal.
That means the value of the Q pi fm will increase.
Yeah. Obviously, value of
Q pi fm.
5 FM.
Yeah.
Exactly. Means 5 FM nahi.
No.
See, under up to this position of the Fermi level, what is happening? Electrons are getting shifted
So
here,
the
right?
value of a Q axis change now from 4.1 to 4.15, I think.
Not getting.
The
4 point.
value of Q phi fm is
Uh,
4.12,
uh,
and for the copper,
uh,
the Q phi fm is change,
uh,
right, sir?
uh,
Then the Fermi level will shift towards the valence band.
Fermi level will.
Valence band towards the valence band.
Yes, so what I want to say is if the metal work function is up to
There,
here,
yeah,
right?
right, sir.
Under up to this line, electrons will get shifted towards semiconductor, silicon, I mean in this case, and there will be depletion.
Depletion.
Right? If
Okay, sir.
you go
Fine.
below this point, what will happen? Reverse will happen.
Reverse.
There will be accumulation then. Electrons will come towards metal, right? And electrons getting out means generation of holes. Then more generation of holes. More
Okay.
generation of holes means accumulation. So band will bend like this now. We will say that initially the structure is under accumulation. However, under this case, I would say it is under depletion.
Sir.
I hope I'm not getting whether you want to say anything else or like this. So both the things are possible, accumulation and depletion depending upon the work
Types
function.
of metal.
Yeah, type of metal.
Types of metal.
Yes. That's why we study separate topic like metal
Okay. And
semiconductor.
sir, the width of oxide layer will also change, I think.
Width of?
Oxide layer.
So it no, that is fabricated, no? So suppose we have fabricated 1 micrometer oxide, how will
Yeah.
that change?
Sir, according to the types of metal, now, sir, it will also change.
Means need to change.
Need to change.
Need to change, no?
Okay.
But once fabricated, then we cannot change.
We can't change.
Obviously, we will calculate it from that oxide capacitance. So oxide capacitance is epsilon on that dielectric permittivity of oxide divided by the distance. So we can from the observations or requirement, we will first calculate what is the COX capacitance per unit area required, right? We know dielectric permittivity of oxide. Determine D from there,
Okay. Fine.
right?
Thank you,
Is
sir.
that clear? Yeah, discussion
Yeah.
should be very means there should be no like confusion. Okay, so both according to his question, both the possibilities are there. Electrons might get shifted either this way or that way. In this case, if electrons are getting shifted towards semiconductor, there will be depletion. If reverse happens, there will be accumulation first. The first we have to make the bands flat, right? We call that as flat band voltage. Okay, so this is discussed. Yeah. Now, as I said, under that condition, what will happen? Everything we have discussed here, only thing remaining was the bending now. So as I said, electrons will shift towards semiconductor here. That means holes will get reduced at the surface, so valence band will move down, right? Valence band will move down. Why? Electrons have you can say neutralized certain holes there. That this is the energy band diagram under that scenario. That way when metal was aluminum and 4.1 electron volt, whatever that is. So we can have calculation for these. So again, as I said, flat band voltage is there, right? So just like his question, we have band bending depending upon the metal, whether bending upwards, bending downwards. So first we need to do is make it constant throughout. That condition we call is flat band. Now we are not in ideal situation. What was the ideal situation? When Fermi level was same for metal as well as semiconductor, right? Now we are in a practical situation. So how to get flat band condition? So what will be the first gate voltage? First gate voltage that is required to be applied at the gate will be the difference between the work function of metal and semiconductor. I hope you are getting this point. First portion will be this one. Difference in the work function of metal and semiconductor. Okay, so that is a story about flat band. Now, what is the other possibility? When we fabricate the structures, there are defects in the oxide. There are charges in the oxide. Now, can anybody tell me again if suppose in this structure, if we have say positive charge at the oxide, if we have positive charge at the oxide, positive charge at the oxide, and my target is to invert the surface, means I want electrons in the surface. I hope you are getting that point. We want electrons at the surface, and this oxide, assume phi m equal to phi s situation. Should I switch to another where I had that? Yes, suppose this is the situation, right? Phi m equal to phi s. Now at this point for flat band, zero voltage is required at the gate. Is that okay? My question is, suppose this oxide is not ideal one now. It has positive charges, say. So in order to invert this channel now, invert means this is p type, na? Invert means I want to make it n type. What will happen to that voltage? We already have positive charges. What is the definition for electric field? Electric field will always originate from positive charge and terminate at negative charge. That means if I have one positive charge here, it will generate one surface electron anyhow. If I have 100, there will be 100 electrons at the surface. So I want to say that what will be the flat band voltage in this case? That is negative, right? Because they are already, these charges are getting electrons at the surface. So now if I combine two factors, difference in the work function and those oxide charges, now flat band condition becomes phi ms minus whatever is the charge divided by the oxide capacitance. Why that? We know what is the voltage and the capacitance charge relation, that is Q by C. Q by C. I hope everybody knows this. So Q by C. So the voltage reduction for flat band will be how much? Q in the oxide divided by the capacitance of this oxide. So what is the net flat band voltage then? Phi ms minus. Is it not possible to have that one? That means some marker and board, no? But still board is not there. Okay, okay. No problem. Leave it, leave it. Okay, so net flat band voltage required now is phi ms minus that volt. That what? Oxide charge divided by its capacitance. Okay, now moving a little bit faster. So what are the possibilities now? when we apply gate voltage, there are three possibilities, right? We can have accumulation, we can have depletion, and we can have inversion. So if the substrate is p-type, obviously we will have to apply a positive gate voltage, ideally speaking, positive gate voltage. Okay, so but before that we have flat band voltage also. So gate voltage required to make the bands flat in the semiconductor is called flat band voltage. So first part for any you can say, we say that threshold voltage, right? Threshold to invert the channel. So first part is flat band voltage. Then what will be another part? My motive is to invert the channel. First part is flat band. Flat band means 5 ms minus oxide charge divided by oxide capacitance. This is okay. This voltage I have to apply anyhow. After that, I want to invert the channel. What should I do? First there will be depletion, right? First there will be depletion at the surface. Depletion means holes will get away from the surface. So what will be generated? Obviously depletion charge. Should I wait? Yeah. Yeah, okay. Okay, thanks. Okay, so as I said, so we have metal, oxide, this is semiconductor, this is p-type. I want to make a n-channel MOSFET. Why? I want to make a, and I am drawing a very, you can say, non-practical kind of diagram, but I want to clarify certain things, that's why, right? I will make it n plus, I can make it drain depending upon its voltage. I can make it source if I will ground it, right? Now when will current flow? When will current start flowing in this structure? This is p-type substrate. It has holes. When will the current flow? Yes, when we will have electrons in the channel, right? So obviously, generally we will have to apply some positive voltage, and that too we can say greater than that flat band voltage. That's what I want to say. So far, what was flat band voltage? This is flat band voltage, right? What was that? It comprised of two parts, phi ms. It might be positive or negative depending upon the work function, right? Like in that case, I think it was getting negative. Okay, so and whatever what I said, there are charges in the oxide. Charges in the oxide may be due to how oxide is achieved by oxidation, thermal oxidation. So all the bonds are not intact, right? We have dangling bonds as well. They can make oxide charges, and some mobile charges also occur. So whatever is the oxide charge there, and please make it very clear that we are talking about positive charges. Context should be very clear. If it is negative charge, we have to put a minus sign. Okay, divided by this oxide capacitance. We can call them per unit area as well, no issues, because both are in the numerator and denominator, divided by area, no issues. So first part is this, at least I have to apply this voltage. Then other thing, what will happen? Okay, I have made the bands flat. Now I need to invert the channel. So first what will happen? First what will happen? There will be depletion first. It cannot invert initially because there are number of holes at the surface as well. As I said, how a p-type semiconductor is formed? So say acceptor atom accepts one electron, it becomes acceptor ion plus creates one hole every time. So I can represent this by this and okay. So for every hole, what do we have? Are you getting? For every hole, I have one acceptor ion. Acceptor ion. For every hole, we have one acceptor ion. Okay, now I said first there will be depletion. Means what will happen? Electrons will recombine with the holes and it will become neutralized. You know, hole is deficit of electron, right? What will be left behind? These charges. Not, but unfortunately they are not free charges. They are fixed charges. Fixed charges mean depletion charge. We call that, and we can see this is the depletion charge, right? So there will be another factor, that is another voltage. We are not under inversion, still we are under depletion. So what will be that factor? We have to add this depletion charge I am representing by qd, and again divide it by the side capacitance. So qd, what will be qd? This is negative charge, obviously qd is a negative charge, and if I will multiply it with nd, if I will keep nd only, nd means only number is whatever is the doping concentration, number per unit per volume. So what I should do, I should multiply it with q. Now it becomes charge, but per unit volume. If I want to make it per unit area, nothing else, just multiply it with w. So like that, we analyze the things and we derive. I cannot derive everything right now. We are not in that situation. But another part of the voltage is this one, right? Still we are not in strong inversion. So I hope you are trying to get. So this is Fermi level. This is valence band. This is valence band, and suppose this is EI, EC. Need to remove this. Is it visible? Suppose this is EC. Where will be EI? Somewhere here. This is the situation for P-type. We know very well Fermi level and valence band are closures of P-type, right? Now, due to band bending, suppose band bending takes place and it reaches here. It means this EI reaches EF. EI reaches EF. So do you know how much voltage is required to do that? 5F, obviously Fermi level, that we call KT voltage है. KT by Q, KT by Q, Ln, and we know very well this is N A. Whatever is P concentration divided by Pi. P is ND, sorry Na. This P is nothing but Na, this Pi is nothing but Ni. So this much of potential is required from the gate up to this point. But what do we want? We want inversion. At this point we can say that Ni is equal to Pi is equal to N is equal to P. It has almost become intrinsic at the surface, right? We want further. We have to invert it. Invert means whatever is the distance between EF and EIE, this EV, same should be the distance between EC and EF. Bending will be there. So it has to bend further. By how much? Again by 5. So that now conduction band, this now what is the scenario now? What is the scenario now? Earlier EI was above EF, right? Now yes, now EI is below this EF. Or you can say conduction band as is closer to the valence band. Sorry, Fermi level. So it has been inverted. It has become n-type at the surface. That's why we call it inverted. So again, another part is this phi f plus this phi f. So third portion is 2 phi. Well, that's how we arrive at the derivation of threshold voltage. Flat band plus this charge, oxide charge plus depletion charge, and then 2 phi f. That much of voltage is required at the gate. I hope some of you might have got that concept. I'm sorry that is difficult to make these things understand from, say, suppose people are from computer science background, then that is very difficult, I guess. Okay, so now we have I'm discussing one by one, like the accumulation and depletion and inversion. So first situation is accumulation. As I now we should be very smart. Accumulation means Fermi level getting, means valence band getting closer to Fermi level even a p type semiconductor. So accumulation band diagram should be like this, right? And as I said, Fermi levels has to be aligned. Then now I have started applying this voltage. I am here. Flat band is made. Now I want to deplete it. So deplete means we will start. How much I have to deplete? How much voltage? Phi f up to here, and further we have to apply phi f more. So twice phi f. Okay. So where will be the band bending? Now see, conduction band is approaching Fermi level because we have to invert it simply. And here you can say that as I explained there. Now EF will come below. Sorry, this EI will come below EF. Sorry, EI will come below EF. Conduction band will. You can verify it from here. Okay. So this is the analysis that we do. I will not go into this depth. Okay. So this analysis is used to derive this charge and threshold voltage. So when Vg is met sufficiently large, what will happen? We call that as inversion. Inversion means now Fermi level is above intrinsic level. Okay, can anybody tell me what will be the maximum depletion width? Can you see from this discussion, what do you observe? What will be the maximum depletion? Maximum depletion means after that there will be strong inversion, right? Maximum depletion will take place first of up to 5F and further up to more 5F, because in this during this time there will be inversion as well as depletion both. So total depletion will be this one. I hope you know that formula for depletion width. Yeah, it is written there. 2 epsilon upon QNA multiplied by voltage. So what is the voltage? 2 phi f, right? So that is the depletion width. This one. कहाँ रखा हो? This one. Means it will not get depleted fully, it will stop at some point. Then there will be inversion only. So finally, do you agree with this structure and its basic working, like how electrostatics is analyzed in this structure? So we have metal, oxide and semiconductor. Okay. In the depletion region, we can say the number of free charges are reduced. Number of free charges are reduced due to the decomposition process. Free charges means I'm not getting. Holes. In the depletion, yeah.
Maybe holes or electrons.
No. So we have to be very specific. See, this is P type, na? P type means majority of charge carriers are holes, right? So depletion means obviously deplete. What is the definition of depletion region? Is that it is depleted of majority charge carriers. Yes. Right. In diode also, we should specify very clearly that depletion region means depletion of majority charge carriers near the junction, that region. Not charge. It has charges, but minority. Diode also has charges in the depletion region, but they are minority charge
But sir, the
carriers.
current flow due to the electrons only, na sir?
Okay, so please, if you don't mix like electrons and holes together. Obviously, we know that. What I said. Now, let me clarify. Right, this is you are very right that conduction will take place due to electrons only.
Yeah.
You know that. Generally, we assume that hole is a particle and it will move. In order to make the thing simpler. See.
Because sir, the mobility of the p types is very less.
Yeah.
In comparison of
around
electrons.
1/3.
Yeah.
In case of silicon, it is around 1/3 as compared to electron.
So the current will flow due to the electrons only.
Current will be not in means everywhere. Yeah, current flows due to electrons only. As far as current flow is concerned.
So the number of electrons are reduced due to the recombination process in the depletion mode.
No.
No, sir.
Not in this case.
Sir,
that's what
you
I'm
have
saying.
explained now where the charge carriers are recombined with each other, p types and electrons.
No. Okay, so no problem, but we should discuss doubt very clearly.
Sir,
What I said is.
Yes, this one. Yeah.
This one, na?
No, sir. Above. Yeah.
Okay.
Yeah, this one.
Let me elaborate that point again. So in P type, we will be adding an acceptor atom. What will it do? Now go to the its basics first.
Right, sir.
An acceptor atom will accept one electron. And it will become an acceptor ion that you are representing here, right?
Right.
And at the same time, it will have one hole. For every combination.
Right, sir.
Okay. Now, that means at the surface, again, please, your question is very good, right? At the surface, we have, so I am representing this by a circle, right? Okay. So for every circle, I have one hole. For another acceptor atom, I have another hole. Now I will call it ion rather than atom, right? Hole and hole. This is the situation at the surface. Now, what is happening? As I did earlier, electrons are coming from the same from gate side. Electrons are coming in the p type substrate. What will happen? This is a common tendency. Whenever an electron will approach hole, it will get recombined and representing a neutral atom, right? So neutral means it is no charge is there now. Electron came, no charge is there. Electron came, hole is depleted, or you can say recombined, right?
Yes.
Or recombined. So what is left behind? Only acceptor ions are left behind.
Only electrons.
Only acceptor ions, not electrons. What I said, these are fixed ions. They cannot carry current.
Okay.
They can generate electric field only. Right?
Right.
And our target is to invert the surface. Invert means I want mobile charges, means mobile carry. We want electrons here. So there are two processes. First, get the holes away. Are you getting? First, get the holes away. So this is done. See, we know hole concentration is how much? Yes, again, no problem. We can discuss many times. Ln, or simply, if I will discuss in this. Yes. So EI minus EF is how much?
Na KT by Q ln Na upon
KT by Q ln
Na upon Ni.
ठीक है, P upon Ni or Na upon Ni, whatever it is, right?
Right.
Up to so what is going on? Electrons are coming at the surface and what is the recombining with those holes and generating depletion charges. That surface is depleted. This process continues here. At this point, when this much of gate voltage is applied, what will happen at this point? Now at the surface, right? Please note this point that at the surface we have now N equal to P, and that should be almost equal to, as per this should be almost equal. If we will apply further voltage, now the situation will reverse. Situation will get reversed because this is Fermi level. and we are getting EI below this. That means we are trying to get like N type, although we don't have N type, right?
Okay.
But why did this happen? Because of the gate voltage, applied gate voltage. So now these electrons at the surface, if I will go more than this, that is phi f up to here, phi f more to phi more than that, I will get a strong inversion. Okay, in some of the books, they specify it up to phi f only. To phi f means all these voltages, flat band plus depletion charge plus oxide charge plus 2 phi f. However, there are some more, like Yanis Sibidis book is there. It will say that under this strong inversion, there should be more voltage, still more, not very much. It's around zero point 0.6 kT by Q, right? But we call that as a surface voltage. Little more for strong inversion. Because after 2 phi f, what happens is depletion stops, right? And inversion starts, strong inversion starts. So for that we require further more voltage. That you will find in some text, some literature. I will like give you the links for those. Otherwise, in most of the books, how much is given? Flat band plus depletion charge plus oxide charge plus twice pi for strong inversion. Now, as you said, the conduction will take place due to electrons, obviously. No issues with that.
Thank you.
Okay, so we have arrived anyhow at this structure. This is called MOSFET, metal oxide semiconductor field effect transistor. And so far we discussed two terminal only, and we have, what do we have? We have third and fourth also. Okay, do you know which will be drain, which will be source? See, this is symmetric, na? Wherever I will, and this is P type, that means I want N channel MOSFET. If I will apply positive voltage here, it will become drain, right? Because it is symmetric anyhow. If I will apply positive voltage here, it will become drain, correct? See, now I want you people to watch this picture and whether it is correctly written or not. It is cut off. So which voltage decides that it is cut off? This one. What is that? The gate to source voltage is below threshold voltage. What did we say about threshold voltage? What was threshold voltage? Threshold voltage. So it would have been up to flat band plus what else? Hmm? Q oxide charges, discharges minus Q depletion charges by oxide charges plus twice 5F. So if this much voltage is not there, that is cut off, right? So this is very clear that it is under cut off, irrespective of the drain and source voltages. Now, what will happen under this situation? It is grounded, it is grounded, it is grounded. It means, I hope now you know, source, drain, substrate. Now gate voltage is more than threshold voltage. What will happen? Just like whatever we have discussed so far. Threshold voltage is this, strong inversion is there, channel is there. It is ready to conduct. Right? But as I said, there is no current flow so far. No current flow. Channel is ready there. You can see this lamp. Yes. But drain and sources are not well defined from outside. No voltage is applied. So what will happen? No current will flow. If there is no current flow, Fermi level will again remain aligned. This you please note down. Yes. If there is band bending, there is built-in potential electric field. What I say, if bands are flat, no electric field. If bands are banded, then electric field is there. And if Fermi level is aligned, no current flow is there. if we have different Fermi levels, that means current is flowing. I hope you know that. Okay. Now, under linear region. So I hope you know those characteristics very well. Na? If what we have done, we have generated the channel here, created or inverted the channel here, whatever it is, and drain is connected to ground. Now I will apply a small drain voltage. Right? What will happen? So obviously, what will happen now? Yes, so those electrons will start flowing towards the drain, and that's why we call this name. Drain means, just like a water supply. So one is source of water. Come to that tap part. It is coming from the source side water. Yes, and the bucket at the bottom will act like a drain of that water, and that means a knob will act like a gate. Simply. So see, what have you done? You have put a bucket here, and gate was already on because you have more than threshold voltage, right? So water or here analogous electrons will start flowing towards the bucket or drain, right? So I think it is clear. No need to explain it too much. I wanted to explain that part because we know this already. Some of us we know that. If I want to plot ID versus V and I will say DS, although source voltage is already zero, what will happen? So when drain voltage was zero, nothing was happening, right? I have applied a small drain. Suppose I have reached up to this point, so it will start increasing. Yes, it just not exactly, but we can approximate it to be linearized for some. And if we will further increase, then what will happen? So as we can see, at this end, electrons will get more electrons will get drained off, right? From this point. It is just like, suppose I have a water pipe, right? It is thicker from here and thinner at this end, right? So the net amount of water coming out will depend upon this edge, this front one. Are you getting? From the behind, from up to here, this is thicker. But now it is limited to this. So water coming out will depend upon this capacity. So same thing happens here. We call that a channel pinch off. This part will become thinner and the current will be decided by that. So, see, please remember that pinch out means it doesn't mean that there is no channel. It is never there. The only thing is it is the most thinnest at the drain end. Otherwise, how will current flow? If there will be zero electron density, then how will current flow? There are electrons and number is compensated by velocity, higher velocity. Okay, so it goes like this ideally, not practically. So if there is no pinch off, then current will saturate, right? If there is no pinch off like this, if it is uniform throughout, then current will saturate. However, due to pinch off, what happens? There is certain slope in that, and this gives rise to the output resistance of the MOSFET also. RO we call that. Otherwise, what is RO here? Can anybody tell me? What is output resistance in this case? So see, resistance means change in voltage divided by change in current. What is change in? We are going to change the voltage. It is there. It is some finite value, say K, constant. However, there is no change in the current. So what is resistance? Infinite. And that is how an ideal current source should be. Ideal current source what should it have? Should have, it should have infinite resistance, right? But practically it is not there because of this pinch off, or we call that a channel length modulation. I hope you know that concept. So, what will be the value of saturation current? So we have for value means you want formula, no? Yeah, so we have formula for that. I think it will be here. So we have linear region. So in linear region, what is the formula? Mu, and I don't memorize it exactly. mu n. So you know this mu n if it is n channel, right? Mu n COX. What is COX? Dielectric permittivity of the oxide divided by whatever is the thickness of the oxide, and W by L. So width part we generally do not draw. Width means how much wider it is along the wall. Okay, so W and length. So length is this channel length, and then we have what is that? VGS minus VT, right? VGS minus VT, and then we have VDS. I hope it is okay, and then minus. Okay, then we have VDS by 2. Should it be square or not? Yes, it should be, because this is voltage and this is, they are multiplied together. Dimension should be correct. It has to be square. Correct? So this is up to which part this is? This is the formula up to here. What is this voltage? VDS. When VDS is less than how much? VGS minus VT. So this plays the role. When gate to source voltage is less than so in case of field effect transistor we call that VP, pinch off, right? Yeah, but in case of MOSFET we call it threshold. Threshold means now we have means there is strong inversion. In case of JFET, what happens? Field effect transistors. Suppose I have N type material here, and suppose I have P type here, right? And I have P type. Suppose I will apply positive voltage here. Again, what will happen? This will be drain. This will be source. So what will happen if I am going to increase positive voltage here? Sorry, if I will increase negative voltage there, and also negative volt. This is reverse bias. Reverse bias, obviously, because see N is becoming positive and P is becoming negative. So it will get depleted. This will also get depleted. This depletion will increase with this negative bias, and a point will come when there is pinch off. Their current saturates. But that is case of FET, field effect transistors. JFET, junction field effect transistor. Here we don't have those kind of junctions. So in MOS situation is little bit different. See, this is also a good point of discussion. What we wanted to do is we wanted to isolate this gate now. Basically, this is creating problem. This junction field effect transistor. Basically, we are concerned about drain current. We are not interested in this gate current, right? So what we did, we totally isolated this. We totally isolated gate from the channel, just like this. Isolated means we have put an insulator there, so that it is not going to dis. Huh? Yeah, obviously, it is more insulated because we have put an insulator, right? So, see, I will discuss one more story behind this. Although this is not mentioned in the books, maybe I'm wrong, but what I think is, in case of BJT, what we do, BJT action is, if anybody is, I think everybody knows BJT, right? BJT. So whether it is NPN or PNP, IE is equal to IB plus IC, na? And current gain is how much? The most favorite current gain for the amplifier design engineers.
Yes, current.
IC by IB. And we want this to be maximum. So how is that possible? We want this to be minimum. Sometimes in solving numerical problems, what we do, we directly write IB is equal to 0. It is totally unethical. Right?
Yes.
So we want this current to be 0. So in MOSFET, this base is analogous to what? Gate. So we totally isolate it. Rather than creating disturbance, we isolate it just like this. It becomes simpler. Generally people say that MOSFET is simpler as compared to BJT. In BJT there are complications, but there are trade-offs. BJT is faster as compared to MOSFET, but MOSFET power consumption is small, MOSFET area requirement is small, and nowadays means everything is done with MOSFET, but BJT is not
But
complete.
sir, the structure of MOSFET and BJT is different.
Yeah, obviously.
Yeah, and the MOSFET is very complex than the BJT.
No. MOSFET is very simple as compared
How,
to
sir?
BJT. Because see, in BJT you have three regions, right? Three
Two
regions.
junction.
Base,
Yeah.
two PN junctions
Two
are
pin
there.
junction.
That is okay. The fabrication of BJT is very typical. We need a base region. Imagine how many wells will be there. Okay, simply I started with a well. Na? Suppose we have n channel MOSFET. I require one well. Suppose I have a P channel MOSFET, I will have an N well. Now, I want to create collector region, base region, emitter region. I will need an extra well there to create that region.
The fabrication process is easy.
Fabrication process is
Easy in the MOSFET.
MOSFET, yeah. Obviously. Everything is about fabrication and
But
area
there are the
requirement.
multiple layers in the MOSFET, like it's a substrate, SiO2 layer, then metal layers, and then channel.
Yeah. If you will see the overall structure of a BJT and a MOSFET, area requirement is much larger
Very
in BJT.
in BJT.
Yes, because as I said, we need separate well, kuwa for like base and collector. Here, that is here. We simply do it by doping. Here, there is no well,
Sir,
na?
there is one question. Can we design the BJT with the help of two diodes?
Okay, so this question, yeah, we generally ask at BTech first year level, right?
Yeah.
Obviously, back to back connector. But yeah, I like to answer this question. It is a very good question. Ever small
Ever small
spent
model.
spent his
Yeah.
entire life, I think, to answer that question.
Yes, sir. Ever small model.
He proposed his own model. Okay, so how does a BJT look like? BJT. So suppose this is emitter region, this is the base region, and this is the collector region. You can clearly see the difference, right? Suppose this is N, this is P, size difference. What is the importance of emitter region? Means how it should be designed. It should be designed with highly heavy doping. What is the requirement of collector?
Lightly doped.
That is secondary, but it should be largest in size. Why collector has to be largest in size? It is just like
To
picking,
dissipate the heat.
just like collecting mangoes. I will throw a stone towards a mango tree, right? And I want maximum collection. What should I have? I should have a broader, you can see it, in order to get more collection. Simple concept. And simply current is I equal to N E A. Area is always there, whether diffusion current or drift current. Area factor is already there. Now, you said diode.
Yeah.
So suppose I have, so this structure is clear to everyone, N, P, N.
And
With this very large, this very small.
yes, sir.
And that is the problem that we cannot get. So if this is P, this is N, and then this is, yes, obviously we will have to do it like this, no?
Okay,
End to
sir.
end. You are connecting end to end like this. So how is this possible? See the size of the base. Size of the why
If
base
the
has to
size
be,
of base area is increased,
yeah,
when you compare with the emitter and collector,
yes, and
then size of the base
we
is increased.
wanted base current to be as small as possible. Base current to be as small as possible, and we have increased the base area, so it no, it can work, but it will not behave as an amplifier. We cannot, in fact, we should not say it as a transistor simply. Do you know what is the definition of transistor? Can anybody say? So sometimes it is being transistor cap. I think we will not be able to switch to the research part. But okay, this is a healthy discussion, means I am enjoying it.
No,
If
no
no
issue, sir.
problem, na? Oh,
No
then
issue.
it's okay. So okay, what is transistor? Simply by definition, transistor.
Transfer of resistor from high potential to low potential.
हाँ आप देखो, let me elaborate this, right? Transfer of resistor.
Resistor.
So rather than putting this off here, I should say only transfer resistor. अब कैसे? Do you know?
Yes.
Suppose I have emitter base collector, say N, P, N. Okay, everybody know emitter base. What we do in general, in active region of operation, if I want to make it active rather than passive, what should I do? I should forward bias, na? Forward bias. Now you tell me forward bias resistance will be high or less as compared to reverse.
Less.
Resistance I am saying.
Less.
Resistance of forward bias.
Less.
Yeah, obviously. So forward the diode is there, right? It is not a special thing. It's just like a PN diode. And in reverse bias, this is the situation of the current until or unless there is breakdown. So please call this as current and call this as voltage, right? So in forward bias there is small resistance. That's why current is very large. Right? In reverse bias there is larger resistance. Okay, I hope it is visible. And what we do with the collector base junction? Okay, see, suppose 100 electrons are emitted, very impractical thing. Suppose 100 electrons are emitted and 5 are recombined in the base. How much remain? How many remain?
95.
95. What do we want? We want to collect them. How will I collect? I will have to
95.
apply positive voltage.
Positive voltage.
That is the only way. So positive voltage to collect these electrons, right?
Okay.
And unfortunately, what do we say? This junction is reverse bias. Yes, obviously it is reverse bias. So what is the resistance here? Obviously reverse bias junction will have higher resistance. Yes or no?
Yes, sir.
Reverse biased. So just like those characteristics. So that is the transfer of charge carriers.
Breakdown.
Transfer of charge carriers from this region which had small resistance to this region which has high resistance. That is transfer resistor. Okay, and basically it is just like supplying energy, means supplying heat from a colder body to a hotter body. Newton's third law of thermodynamics that refrigerator works on. We are supplying energy, means the heat is taken out of a colder body and transferred to a hotter body. How is that possible? Work is required to be done, and that work is done by that voltage VCC. Okay, so now where were we? I forgot. We were now. So is the thing clear?
Yes, sir. Clear, sir.
Okay, so the question was diode and to end. Yes, obviously it is not possible. We have to transfer, in order to have a transistor action, we have to transfer charges from carriers from small resistance area towards large resistance area. There it is, everything is
But
destroyed.
sir, we are taking the principle of diode to explain the BJT.
Yes, because that is very, because what is here? This is forward bias PN junction. We have a depletion layer. Depending upon the doping level, we will have extension of the depletion layer. Obviously, it will behave like a diode. It will behave like a diode. This will also behave like a diode, but it will not meet that structure. Where was that? That end-to-end connection. It will not meet the requirements of a transistor. What do we want in a transistor? We want IC to be large, IE to be also
Base area
large,
should be very
and
thin.
IB to be very small, ideally zero. It is not able to achieve. We are not able to achieve that in case of end-to-end connected diodes. Right? They are not fabricated as well. That strategy. Okay. Yes, so now in linear region. So in linear region means a MOSFET in linear region means we always focus about this in linear region. This one. So please never get confused with the regions in MOSFET. If we talk about inversion, means in that context, so there may be accumulation, weak inversion, depletion, strong inversion. And if we say linear region, so linear region means we are talking about ID and VD characteristics. This part is linear region. Beyond that we have saturation region. Okay, so linear region, how is that defined? When drain to source voltage is less than the gate to source voltage minus the threshold. I hope you know these voltages. Gate to source means whatever is the potential between gate and source. Generally source is grounded, and minus VT. All that I discussed. I think for more than half an hour I discussed VT. So that reason is linear. If I want, I will increase VDS. Beyond that, I will be in saturation. Here it is. This VD set. VD set means now I have increased my VD to this point. Okay. So what will happen? That was the point of discussion. At this point, what happens? The channel near the drain becomes very thin. Okay, very thin. Now, can anybody tell me then if channel is very thin, then how current is constant? I explained you with this example. I had explained you with this example. Which example? If there is water pipe, some water is from here, then it is thin, current will be limited by the exit end. Now, in order to compensate for the number, please note down, in order to compensate for the number, what happens is velocity is increased near the drain end. There is more velocity at the drain end. So, what is current? I equal to generally I N E A V D. So, drift velocity is higher near the drain end, number is lesser. Anyhow, that current becomes saturated, but still it does not saturate, as I told you, because of that channel length modulation, pinch off. There will be some slope. Okay, so yes, generally people so pinch off by this, it means channel is not there, but please never assume that channel is there but very thin, right? Okay. Okay, so what do you say? If channel will not be there, then is it possible there will be current flow? No, channel is there, but it is very thin. Yes. And why it is getting drained off? Because obviously you are applying positive voltage here. Whatever you had done your hard work to invert this channel is now drained out by this drain terminal. Those electrons are taken out. Okay. So this portion they have if we represent it by pinch off, I will say effective channel length now is reduced. I will assume that channel is not there, inversion is not there. So there will be voltage drop across this region or not? In this region, will there be voltage drop? Yes, obviously, we have voltage drop there. So we can go through these points again if you want. So what is this? Minimum voltage. This is, you can say, recap whatever we have discussed. Minimum voltage required to form inversion layer is what? Is what? Threshold voltage. What does it define? It defines operation of the MOSFET, whether it is on or it is off and how much on it is. Okay, but rather than saying how much on, I should say how much off it is. Nowadays, people face difficulty with not turning it on, but rather turning it off because of the leakage currents in the off state. Because in off state we have weak inversion also, moderate inversion also. We talk only about threshold voltage. On means more than threshold voltage. What about off? Off is also not abrupt, no? Off is not abrupt. There are some leakages. Okay. So this is not absolutely right statement, the last one. When VGS is less than threshold voltage, current still flows. We call that as leakage current, unwanted current. Okay. So, can anybody tell me now that what are the 4 physical parameters we discussed? 4 physical parameters that define threshold voltage. We discussed them one by one. Metal semiconductor work function, then oxide charges, then depletion charges, and then how much is phi f, that is doping level. Okay, so just I will not go through these derivations, right? Not required, I think. They are in the book. Everybody can go through those. Just write. Should we solve problems? We should solve problems also. So okay. So meanwhile, I will also drink some water and so consider this situation. Let it be. We don't have that much of like pen. Suppose consider the MOS system with following TO oxide thickness is 200 angstrom. This is you can say phi ms, right, minus 0.25. Accepted doping is this one. What is this QOX? Oxide charge. And as I said, assume it to be positive. Here it is already given positive. Determine threshold voltage. And why do we say this room temperature every time? It is required. KT. The KT factor is there, so we require this. And epsilon, this dielectric constant of the oxide is, relative dielectric constant of oxide is 3.97 for silicon. So can we solve this now? Can we solve? I think yes. In fact, that formula there. So flat band has 5 ms and minus this oxide. Sorry, there is one problem is there. This part is not there, right? If I will write this, that already occurs under that part, under flat bed condition. This part already occurs here. Flat band has 2 parts. What? Metal semiconductor work function difference minus this Q oxide divided by oxide capacitance minus this depletion charge divided by oxide capacitance plus twice phi f. This is the value of threshold voltage. Can you calculate it? Okay. Okay, so you may note down, and I think that is not a big deal to solve these problems. And then there is a cross question like you have to determine the concentration that is required for a threshold voltage of 0.8 volt. So how will you get that point? You are given Vt, you are given phi ms, you are given this also, and now from where will you get? What is the value of this Qd here? I am repeating this one. This Qd here is this Qd here. See, nothing but the dopant ions. It will depend upon the concentration of the dopant. So how much Qd is there? Are you getting that part? Same. This Qd here is nothing but Q times of those doping concentration. But and also this is per unit area, so we should multiply it with W because Na is per unit volume. Okay, just skip this. Okay, no problem. We will do this. I have solution for this. If you want, you can take it later on. So this part is already discussed. So skip this as well. Derivation. Now You know, everybody knows these characteristics. No need to elaborate them. What happens? So, for example, in this case, I had say any gate voltage, say a VGS1. Suppose this was the situation at any gate voltage. Now, what can be done? Yes, so everything was fixed here. Everything was fixed. Now, I will increase the gate voltage. Suppose I want to increase gate voltage, what will happen? Obviously, this graph will shift. Why? More gate voltage means more inversion. More number of electrons are there now, and number matters there. I is equal to NEAVD. So more electrons, so this will go to some higher, and again it will saturate, just like this. Say VGS2. So it is very much clear that VGS2 is greater than VGS1. If I will decrease, then obviously A1 hai. If I will decrease, then 2 is more than that, and VGS3 it is less than that. Okay. Now, if I want to plot the reverse, VGS versus, because ultimately current is same, drain, I can produce these lines backwards. That is what is done in that picture, right? And I will get graph something like this. They are also called transfer characteristics. I have drawn very roughly. They are also called transfer characteristics. But nowadays we have smart simulators like TCAD. There we can plot ID VG versus ID VD, all the plots we can do. But it means this one actually. They are interrelated. Okay. So that's why this will be called linear region. Which region? Up to here that I discussed. Up to
Sir,
this. Yeah.
is there any breakdown?
Yes. So see, if we will go on increasing VDS beyond the specified limits. So what is VDS? There is N plus drain, then there is channel. So let me call it channel. Channel means substrate is of P type. P type. So obviously we have what? We have a PN junction here. Yeah. We have a PN junction here. If you will reverse bias it too much, the junction will get it breakdown. There will be breakdown. Just like in diode, avalanche breakdown or Zener breakdown. Obviously, avalanche breakdown will occur there. And if that takes place, then nothing is left. What will happen? What will happen then? These currents will increase. We should not operate up to those values. They are always mentioned, specified, right? Okay. So there is another, please go through this for some time because solution is also there and question is also there. Formula na earlier. So this is under linear region, right? Under saturation region, what will happen? What I said, under saturation region, we say that this VDS becomes equal to VGS minus VT. Just modify the formula. What will be the formula in saturation region? So everything will be same, mu and COX, W by L. May put a half there. It will become VGS minus VT whole square. You can check it. By so this two is outside, no problem. If you remember, I had put this 2 here, there was no 2 here, there was half here. Yes. The thing is not about memorizing or just those formulas. Another example is also there. So when will we apply the saturation formula? We will check first. What is the condition for VDS? What is VGS? What is VT? If VDS is greater than or equal to VGS minus VT, then we will apply like this question. What is asked there? If I think if you can understand this problem, then for saturation region what should be there? ठीक है. Let me talk about this n channel MOSFET only. Otherwise it becomes very complicated. There we have to just think from the negative perspective. If in n type VDS has to be greater than, then in p type it has to be smaller. So what you do is just replace everything by its mod value. Then mod value will make sense. Means magnitude of this should be greater than magnitude of this. That's it. In p channel also. In p channel also, right? Okay. So I think these are simple problems. Okay. Channel length modulation is done now. There's some repetition. Yes. So what happens due to channel length modulation? There are two things. This drain current under saturation is this one, mu n COX by 2 W by L VGS minus VT square. Correct. If the graph were like these red ones, then this is the formula up to here. However, if there is channel length modulation, obviously it is there in long channel or short. Is this short channel dependent or long channel dependent? No. Okay, so we have a separate term there, 1 plus lambda VDA. This is channel length modulation factor. So substrate wise, we can change the threshold voltage with the help of substrate bias also. See, once the MOSFET is designed, its threshold voltage is fixed. But if you want to change it from outside, then what is the way? Then the possibility is apply substrate bias. Then we can vary its threshold voltage. Okay. So I think do you know these things? Capacitances. So we know very well what is oxide capacitance, oxide permittivity, COX divided by that. Now if I want to know what is the gate to body capacitance, how do we find that? I will spend little time with this. Then you are not going to listen to my research, that means, right? My research area. That is, I think the time is very, because I will have to build a background for that as well. Okay, let me try to finish it quickly. No problem. Okay, so we have like metal, and then we have say oxide, and then say semiconductor. So it is behaving like a metal plate. Then we have oxide there, and let me represent it by a plate. So it is like a capacitor, right? This is like a capacitor, COX. What is its value? That is dielectric permittivity of oxide divided by this thickness, TOX. I am writing. So this is what is its unit? Because capacitance is generally epsilon A upon D. We know very well. Area is not there. So this is per unit area, right? This is per unit area. So what will be total capacitance, gate capacitance, then gate to body? Total capacitance. I hope you are getting. This is capacitance per unit area, COX. I have to multiply by area. Well, how much is the area? So gate length, this length and width, top, from top side. So we multiply it by W and L. That's it. Now there is one more thing. Here we have assumed ideal dimensions. Suppose there is overlaps. Suppose there are overlaps. Suppose say this is source end and this is drain end. Can you see this? This overlap is there, right? Between gate gate and source and drain. I mean, suppose this length is LD. Now, can you tell me what will be GD, gate to drain? C, gate to drain capacitance. What will be this? So we have gate plate, we have drain plate. Gate plate, drain plate. How much distance is there? Hmm? How much distance between this and this? Again, TOX. In between we have oxide. So what is the capacitance per unit area? COX. But what is the area? So area is how much? This LD multiplied by, and how much will it be? Obviously LD is the overlap. Overlap. You can say, we also say those diffusion lengths, right? Diffusing and multiplied by W. This is the gate to drain overlap capacitance. Overlap capacitance, which should ideally be taken equal to gate to source. You are asking something? Is it clear? This is clear? So these are different, you can say, capacitances. Gate to drain, this. Gate to drain means only overlap part. Gate to source, overlap part. Gate to body, this one. Now, everything you might be knowing. Why CGB is equal to 0? This need to be think. We need to think, right? See, under cutoff, this is okay. Under linear region means channel is there. Why CGB is equal to 0? That is important. Do you think this is wrong? Injustice? Yes, exactly. So no capacitance will generate between between gate and source. So body, means we are talking about this body terminal, or also in saturation region. And rest we just make it half up, right? You can see this half here. We just make it half towards source, half towards drain. This is overlap. Again, half towards source, half towards drain, and overlap. Here, CGD, this, what happened under saturation region, and this. Under saturation region, we will take this as COXWLD. Why? Due to pinch off. Due to pinch off. Source side we will take 2 by 3. We will make it 2/3 plus overlap. And but this 0. Why that 0 is there? Gate to body capacitance is 0. So is it wrong? Is it wrong? The CGB under linear and saturation region. However, under this condition, it is COXWYL. See, cutoff means no channel is there, right? No channel is there, so obviously capacitance is COXWYL. WYL is area. So WL is area. COX, whatever is this oxide capacitance, MOS cap. But once linear region means channel is formed there, that capacitance is screened off. Are you getting? That capacitance is screened off because of this inversion layer charge. So that's why we say that there is no capacitance when it is inverted from gate to body. Overlap part will remain there because it is directly below that. If oxide is here, overlap part will be there. Did you get? And yes, this LD I wanted to show is this overlap. Yes. So what will happen to channel length under this case? If channel length is a LG earlier and there is some because of fabrication mistake or mismatch or default improper fabrication, there is an overlap of LD. What will be the channel length now? Same? Are you getting? So this is source, this is drain part. But you can say this is extended here, or you can say gate is extended towards source drain. So effective channel length will decrease no? By 2 LD. LD this side, LD that side. So these are the capacitances again, just in a 3D kind of view, top view. You can visualize those. I hope now you got this W. This is the W. Long. Right? And what is this now? Earlier that was the contribution of oxide capacitance from gate. But see, this source is N, drain is N type. This substrate is P type. There is one more capacitance. What is that? That is this we call depletion capacitance. Getting? That was overlap capacitance. Earlier we discussed. This is depletion capacitance because PN junction will be there, reverse or forward biased. While in general operation, generally speaking, we apply positive at the drain, which is N type, and generally ground it's obviously reverse bias. So reverse bias junctions are there due to which capacitances are there. We know very well capacitance. What is why are we going through this capacitance? Time is equal to resistance multiplied by capacitance, generally proportional to that. No? So the time taken by any device to function depends upon its capacitances. More the capacitances, slower it is. So from circuit perspective, we want to discuss these parameters. Okay, this is all done. Now, this I knowingly put this slide. What are these? Do you know? All are MOSFETs. Left side we have an MOSFET, and N means N channel, right? And in the right side we have PMOS. Do you know in different books you might find different symbol, right? In some books they just write this one. They will put an arrow this way and arrow. So how will I say that it is N channel? Do you know? Do you know how the direction? What does the diode symbol represent? What does a diode symbol represent? It represents from P to N. Na? Always. This arrow means P towards N, right? This arrow means P towards N. Now to make that N, we put a strip here. Similarly, here, if this is the scenario, these are sometimes confusing. I don't know, should I discuss that or not? What do you think? That means here we have P substrate and we have N channel. So arrow is pointing out, sorry, opposite okay na? N channel, this we will call N. What does this arrow show here in this case? Huh? Current flow from source to drain. Current flows from drain to source. Okay, but there is another way of representing it just like diode. What is that? Do you know? This one. this one. क्या क्या है ये सब? What does this show? The channel is not there, right? So we need to make the channel enhancement. Now there is gap, means oxide or insulator is there. So this is gate. Now, as I said, if I have P substrate here, and obviously P substrate means we are talking about N channel. P substrate means N channel. So where should this arrow be? Tell me. P substrate means N channel. So this arrow should be like this. Are you getting? Substrate towards channel. And also, if this will continue, the current will flow like this. Okay, and that's why we arrive at this symbol. So different literature they have the symbol. We should be aware of that. See, we have, yes, we have it. So this is N channel. See, P to N. Sometimes strange, although this should not be done, because we should show an isolation at least from the gate. But in some literature, you will find this symbol also. You will have to assume this. Okay, and this. So sometimes what they do, they will draw this symbol. I'm knowingly discussing this point. They will draw this symbol and just will mention ID and write NMOS. That's it. This also happens, and this is most common. The first one, PMOS. So there is one way of representing NMOS and PMOS as well. What is that? Do you know? Only that I will discuss for PMOS. If it is done there like this, it is not there. No? This is PMOS. If this inverter is there, inverter symbol is there, that means PMOS. Others are also there. Opposite of that. Now, to conclude this MOSFET, I will say MOSFET is used in analog circuits as an amplifier. Amplifier means to amplify the voltage of the signals, and in digital circuits as a switch, right? So if we will make it off obviously with the help of gate voltage. So we will not invert it, we will say it is off. So there is no channel between drain and source. We will say it as acting like an open switch, right? And if channel is there, no problem. Whether it is PMOS or NMOS, it doesn't matter. If channel is there, what we say? We will say what? It is on. This is already discussed. To conclude, no current flows, then what happens? Drain current increases like this. Why? Because after 2 5F voltage, that all this threshold voltage, there is exponential increase in the current. Why? Do you know? This point should also be discussed. Do you agree? In diode, have you ever thought that why this graph is there? Yes, in a silicon diode, suppose. Diode current versus diode this voltage. What happens? Once the barrier is crossed, right? Once the barrier is crossed, then there is very small drop across the diode. Rest of the voltage drops across the external circuitry. Same thing happens here. Once threshold voltage is reached, right, then there is very small drop across the MOSFET itself. There is all other extra voltage is dropped across the external circuitry. Same thing happens here. Okay, and we know in ID, VD characteristic, linear region, saturation region. This is done now, more than that. You know this now. I will not discuss this again. There is another question. If you want, you can note down those. So should I switch to my research part now? I think sufficient for the basics. Inverter is there, then again it will take. This is complete analog and digital VLSI. Okay. So noise margin, many things are there. Okay, now I have arrived at this slide 0. So far we have done 0. Okay. So first next comes is introduction, and introduction that too of my topic. So what was the topic? NAND flash memory. Okay, charge trap based 3D NAND flash memory. So now you know flash memory. Again, in flash memory we have a floating gate transistor now. That's why this story was discussed here. We have floating gate transistor. Have you ever heard about this? Okay, the MOSFET that we have discussed so far, can we store information there? Yes? Obviously, no. We cannot store, no? As soon as the things are released, electrons will go to their places. Now, if the same MOSFET, I will do like this. See, now please, suppose this is metal, right? Now think about, then suppose there is another, for this time, just consider it as a trap. I will explain it in a while. And then I have, so this one. This is semiconductor. बीच में ऑक्साइड है. Okay, so we have oxide. Suppose we have such kind of structure right now. Forget about source drain. This is just like MOSFET, na? Just like MOSFET. What do you observe from here? Suppose this is P substrate, no problem. What do you think now? What will happen if I will apply this gate voltage and increase it? What do you expect? Just simply whatever you have learned so far. So after threshold voltage, what we have? After threshold voltage, we have electrons here. I want to increase it further. Don't worry. Suppose I want to increase it up to 20 volt. Don't worry. What will happen? ठीक, more, okay, it will be. But our purpose is something else. I want, is it possible for this electron to enter here? Possible. And see, oxide is there in between. So obviously, we are struggling with this difficulty in a normal MOSFET also. In a normal MOSFET also, I hope you know that. In a normal MOSFET also, we are always concerned about this. What do we call this current? Gate leakage. Like some of the electrons, they cross this oxide and enter gate. Okay? Do you know this? Leakage current. Means Ig is perfectly not equal to 0. We utilize this concept. We trap electrons from channel in the trap layer. And now you see, if all the voltages are removed, see, if all the potential voltages are removed, what will happen? This electron will stay there even for 10 years. There is no way of leaving it. Means it will not get released either to up or down. Why? Because we have insulator here. Here we have insulator, but it is trapped here. So that is how this comes into like memory element. Okay, and we call it as floating gate. Floating gate transistor. So why floating? Because this is not electrically connected to either the substrate or to metal. That's why floating. So this is the principle of operation or working of my research topic that I have done so far. This is very basic structure. I hope you got that. Now, so this is called write operation. This is called write operation, right? And also I will call this as program. I want to do another write operation and I want to erase that. Erase means electrons were trapped in that trap layer or floating gate. I want to get it back. What should I do? Yeah, yes, obviously. Because if you will keep it for see, you trapped these electrons and removed this battery and kept it for 10 years. Charge will remain there. Now, if you want to erase it, what will happen? Just do the opposite. Okay, do the opposite. Apply negative voltage there, and it is erased. Got it? Got it? Now see, if this is okay, then I will explain you one thing at this moment. For this transistor, if you are able to understand this, suppose I have VGS and ID. Okay, suppose these were the initial ID VG graph. This is initial. And suppose I have some threshold voltage VT1. Initial means nothing is trapped here. Please try to understand. Nothing is trapped here, right? Nothing is trapped here. We have metal, oxide, this trap layer and oxide, right? And then this is substrate. And normally we have source, grounded, and we have drain. So what say I will apply 1 volt at the drain and fix it, and what will I vary? How do we plot ID VGS characteristics? Anybody? I will vary gate voltage, no? Keeping drain voltage fixed. Now, suppose I will get this kind of characteristics. This was a fresh device. Now, I want to program it. So first I will program it. Program means apply high voltage. से मैंने 20 वोल्ट लगा दिया. लोग घबरा जाते हैं, लेकिन earlier they used to do that. Okay, 20 volt करना है ना. You have to trap electrons here. What will be the mechanism? Obviously tunneling. Tunneling, you know? Yes. That what do we say that tunneling? Which phenomena that is? Which phenomena? Electrons, they behave like particle as well as like wave. So quantum mechanical phenomena. I am very weak in quantum mechanics, but at least I know that the mechanism will be quantum mechanical tunneling. And in fact, there are types of tunneling like direct tunneling, band-to-band tunneling, Fowler-Nordam tunneling. Here we get a mix of direct and Fowler-Nordam tunneling. These electrons are trapped here. Right? That depends upon the this thickness of the oxides. We cannot keep them very thin. Why? Because later on, within 1 year only, that electron might come back. So they have to be kept sufficiently large. That's why. Okay, now did you get this? Was the initial device, just born device, it IDVG characteristic. Okay. Now I program it by applying 20 volts at the gate. Some electrons are there. Say not some. Suppose sufficient electrons are there. Now you tell me, this is programmed, right? I want to do its IDVG characteristics for the program device. Will it be same? Getting? I have programmed the device. Electrons are in the trap layer now. Will the IDVG characteristics remain same? No. Obviously, they will repel. IDVG means we are forming channel. So first these electrons will repel the channel electrons. We will have to apply more gate voltage. So your IDVG characteristic will shift. to say VT2. That means same device has two IDVG curves. This was for the unprogrammed device, this is for the programmed device, right? Suppose this is equal to 5 volt and this is equal to 2 volt. Suppose the threshold voltage of the programmed device is 5 volt and of the unprogrammed is 2 volt, right? Right? Suppose I will apply a read voltage of, that's why I did not decide to teach my topic directly. Suppose I will apply a read voltage of 3 volt. What do you think? What will happen? When device is programmed, its threshold voltage has increased to 5 volt. When it was erased or initial, its threshold voltage was 2 volt, right? I am applying a read voltage of 3 volt. So in which case will it conduct? Tell me. Obviously it will not conduct in this case, no? Means your drain voltage is fixed. Drain voltage is fixed, say 1 volt. You are applying gate voltage. Suppose आपने 3 वोल्ट लगाया है तो क्या होगा? इसका तो threshold voltage of the program device is 5 volt. Why will it conduct? Not conduct, but it will conduct. That is why we call this device at logic 0, right? And this device at logic 1. And that's how bits are stored in the form of ones and zeros.
Sir, can we trap the both charge carriers?
Both charge carriers, sometimes we say that. Both means again, there is no physical existence of holes, right? Anything deficit of electron is called holes. Simply.
It means it depends on the type of material for a trap.
Yes, exactly. So we can store holes also. You are right. We can store holes also. Holes means we have to make here something deficit of electrons. Yes, that is also done. Okay. So, see this picture. What do you observe from this picture? Should I stop or what? You tell me. Time is over. Okay. Then let me explain you. So you got that point, na? Restoring charge. Okay. Do you know this picture? This was generated by this Samsung. Samsung is the memory player nowadays. What does this say? Earlier we were designing memories in 2D. 2D means just on the wafer, right? But now, earlier there were memory cards of around 500 MB. Now we have pen drives of around terabytes, SSDs of around hundreds of terabytes, at least 30 terabyte SSD is there, right? So what happened? So three things were there. First one was material innovation. Okay, please listen to this point only. Material means earlier this trap layer was a floating gate polysilicon channel. Polysilicon was used as the floating gate, and now it is replaced by silicon nitride layer rather than polysilicon. So what I said, polysilicon gate तो आपने कई बार सुना होगा ना, तो यहाँ पे भी यूज करते थे. And now it is replaced by a silicon nitride layer, Si3N4 layer, which has traps, both kind, as you said, it has both kind of traps. Either more electrons are there, negative, or it is deficit of electrons, positive, right? Both are there. So material innovation हो गया. Then structure wise, earlier we used to fabricate 2D or planar MOSFETs. Do you know we have now cylindrical MOSFETs? Right? Cylindrical, this is planar, na? Then why do we go for cylindrical? So suppose this is substrate, I want to draw it like a cylinder. This is substrate, and then I will have like this cylindrical. Suppose this is oxide, and again I will have from outside like this metal. So what is the disadvantage of 2D MOSFET? There are more leakages because of lesser gate control. So we want to make the control of the gate from all the sides, gate all around, we call that. So that's why another change was 2D to 3D, means cylindrical. And the most important was earlier we used to shrink in the XY direction, means planar only. Whatever is the space available to us in any chip, we were just scaling down in that area only. Now what happened, there is scaling along the vertical direction. I will show you how can you think how is the scaling possible along vertical direction. It seems very strange. Suppose this is wafer surface, shrinking along the wafer means in xy plane is okay, minimize transistor size, we will get more number of transistors. How is this possible in z direction? So yes, almost. But what happens is, rather than in the means rather than in this direction, memory strings are designed in this direction. But how? I will let you know how that is done. First of all, holes are etched in the wafer. Downwards, holes are etched, right? And then different layers are deposited. Whatever was required, like this. We had substrate, we had oxide, we had this trap layer oxide metal. Okay, just tilt it. So we will etch holes. Okay, we will deposit silicon, we will deposit oxide, we will deposit nitride layer, we will deposit oxide and then metal. And transistors will be, suppose this is one transistor, this is another transistor, and so on. So recently Micron has released its 230 or 40 layered, and we call it NAND because all the transistors are in series. That is the difference between NAND and NOR flash. In NOR flash, transistors are connected in parallel, that's why it is faster. In NAND flash, transistors are connected in series, that's why it is bit slower, but capacity wise, means connections are made such that it has larger bit density. In the same area, we can store more number of bits. So how should I hope that that point is clear to you. This is the motivation. I think I should stop at motivation, right? Because it will take more time. This one. I forgot to mention SSD there. The application part. You can see flash drives, embedded system, mobile devices, digital camera, and now SSDs. Right? So I think we will meet some another time and discuss these parts also. Okay? Okay.
Thank you, sir.
Thank you very much, sir, for this enlightening session. Okay, now I would request FDP coordinator Mr. Rajesh Singh Sekhapat to honor our distinguished speaker with a token of love.